For section 3.3, we're going to be talking about two basic rules of probability, and the first one is called the multiplication rule. So when we talk about probability, last week we talked about independent events, but sometimes events are dependent, and so then we have some additional things going on, and in fact we introduced this one last week also, what is called conditional probability. So suppose that two events can occur, or we consider these two events, A and B. The probability of event B occurring, given that event A has already occurred, is represented as P, and then you have this parentheses, B, and then this line with an A. And the way you read that is the probability of B given A. And so when we talk about probability of events A and B occurring, the general formula for that is the probability of A times the probability of B given A. And so last week we had our rule for independent events, which just said probability of A times probability of B, and that was if they were independent. This rule, it doesn't matter if they're dependent or not. That will this rule will work for both situations. Okay, this is the rule from last week that only works for independent events, but at the bottom here, this one will work for independent or dependent events. Back to Bucky's deck of cards here for example 315 and his friend Satchel. What is the probability of Satchel drawing a heart, then without replacing the card, drawing a spade? So we're going to have the probability of a heart, and I'm going to abbreviate here, and then a spade. And remember, this is without replacement. That doesn't spell replacement. Replacement. So our formula now that we just learned says that'll be the probability of getting hearts times the probability of getting a spade, given that they already got a heart. So the probability of getting hearts, if you go back to your picture there, I guess I didn't add it to this one, but probability of getting hearts, remember, is 1 out of 4, because 1/4 of the cards are going to be hearts. Then, assuming that we got a heart the first time, what are the chances that he gets a spade the second time? Well, that's going to be 13 spades is how many spades there are altogether. But now notice there aren't 52 cards anymore because we took out that one heart, so that's going to be 51. So if we multiply this, we're going to get 13 on the top, we're going to get 204 on the bottom, and if we are asked to put that in as a decimal, 13 divided by 204 is going to be 0.064. So either as a fraction, which is an exact value, or as a decimal number. Example 316, the deck of cards, Satchel. What is the probability of Satchel drawing 2 clubs without replacement? So this one is drawing the probability of drawing a club and another club. So that is the probability of drawing a club, and then times the probability of drawing a club given that you got a club the first time. Whoops, parentheses. Let me fix that up, parentheses. So again, the probability of drawing a club is 1 out of 4 because 1/4 of the cards are clubs. But the chances of getting a club the second time, given that you already got a club the first time, and again, without replacement, we have only 12 clubs left out of the 51 cards. So if we multiply that, let's see, this is going to be able to actually reduce here, I think, but let me just double check. It would be 12 over 204, and I think that divides in there evenly. It does. It would be 1 out of 17, and 1 out of 17, if we change that to a decimal number, is going to be 0.5, oops, 0.0, having trouble here, 0.059. So again, fraction, 1 over 17, the decimal number, 0.059. So again, this formula works for independent or dependent events regardless. Example 317, in 2005, 19.1% of all murder victims were between the ages of 20 and 24. Also in 2005, 86.9% of murder victims were male, given that the victim was between 20 and 24. What is the probability that a randomly selected murder victim in 2005 was a 20 to 24-year-old male? Round to 3 decimal places. So the probability here, and it may be a little bit deceptive, but the probability is that we have a 20 to 24-year-old individual and that they are male. Okay, so our formula that we'll use is probability of 20 to 24 times, whoops, not minus, times the probability that they are male given that they were between 20 and 24. Okay, so first of all, we are given this information. In 2005, 19.1% of all murder victims were between the ages of 20 to 24. So that's where we get our first number, and that's going to be 0. We have to change that to a decimal, 191. Then for the second part, the chances that they're male given that they're 20 to 24. So 86.9% of the murder victims were male given that they were 20 to 24 years old. So that is going to be times 0.869. And then we're just going to multiply those together and round off to 3 decimal places. So 0.191 times 0.869. And our answer then is 0.166. Rounded off to 3 decimal places. So that is the chances that one of the murder victims was 20 to 24 years old and male. So notice it has to be smaller than both of these numbers because you're multiplying them together. So 19% were 20 to 24, and then 16.6% were 20 to 24 and also male. Example 318, suppose G-Pod manufactures 100 of their new phones, the G phone. I think we might be alluding to something here. Because the G phone is new to the cell phone market, there are an estimated 15 G phones that are defective for the 100 manufactured. OG, the creator of G phone, decides to test 3 out of the 100 phones. What is the probability that at least one is defective? So we learned this formula about at least one last week. At least one, the formula for at least one, so at least one defective is going to be equal to 1 minus the probability that 0 are defective. Okay, so we're going to have, and again, since we're choosing 3 of them, that means not defective, not defective, not defective 3 times. So we're going to have 1 minus the probability that the first G phone is not defective is going to be 85 out of 100 because it told us that 15 were defective, and that means 85 are not defective. So that's the first one. But then when we go to the second one, notice there's only 99 more phones to choose from. And if the first one was not defective, then there are only 84 more that are not defective. Okay. Then when we go to choose the third phone to test, there are only 98 phones left. And if the first 2 were not defective, then there are only 83 more that are not defective. And so when we multiply this out, we're going to get the probability that For this part right here, this is the probability that none of the three that we choose are defective. And let me actually underline that in color. So this is going to match up with this. And then if we want to find out what are the chances that at least one was defective, we're going to subtract that from 1. So let's go ahead and do this work. 1 minus, and I'm going to put it in exactly as I have it written, parentheses 85 over 100, close parentheses, times parentheses 84 over 99, and then parentheses 83 divided by 98. And when we get that, our answer ends up being 0.389. As a fraction, that one would be pretty messy, I think. So I would suggest probably just doing that one as a decimal number. It ends up being 899 over 2,310. So I would definitely go with the decimal in that case. But remember those properties we learned last week, at least one defective. And then how we find this one, this is from today. Those are all conditional probabilities. The chances that the first one is defective, then it's conditional for the second one and also conditional for the third one. The second main property that we want to talk about, again, is one that we alluded to last week, but we were dealing with disjoint events. But here we're going to talk about it doesn't have to be disjoint or mutually exclusive. So this is the probability of either of two events occurring. Suppose that two events A and B can occur, so we're considering these two events. The probability of either event A or B occurring is going to be the probability of A or B equals the probability of A plus the probability of B, and then minus the probability of A and B. And the issue here is if these events are not disjoint and you just add the probability of A together with the probability of B, some of your events have been counted twice, and so you have to subtract out those events that have been counted twice. So that's what the minus P of A and B is doing for us. Example 319. Recalling from example 3.3, Bucky has his standard deck of 52 cards and wants his friend Satchel to draw a card. After Satchel draws a card, he puts it back into the deck. Find the probability for Satchel drawing a queen or a spade. So we're looking for probability of queen or spade. So according to our formula, because these are not disjoint events, there is a spade that is a queen also. So we have to do the probability of a queen plus the probability of a spade, and then minus the probability that it is a queen and a spade. All right, so probability of a queen, remember any one type of card, we have 1 over 13, plus the probability of getting a spade, that's a suit, so that's 1 over 4, 1/4 of the cards fit into that group, and then minus the probability that it's a queen and a spade, well, there's only one of those, so minus 1 out of 52. So it might be easier to change these all out of 52. This is 4 out of 52, plus 13 out of 52, minus 1 out of 52 will give us 16 out of 52. And then if we're going to use this, we would want to reduce. That'd be 4 out of 13. And if we change that to a decimal number, if they're asking for that, we would get 0.308. Okay, so if they ask for exact, it's going to look like 4/13, the fraction. If they ask for rounded off, we're going to put 0.308. That is the end of section 3.3, so make sure you're working on those, and if you have questions, please make sure that you check in with me and ask.